So basically, if we compare what is habitat and what is ecological niche, basically the difference is that a habitat is a place, but ecological niche is a role. And we define the ecological niche to be the role and the position of an organism within its environment and community, while the habitat is a physical environment where an organism live. So habitat is a place, ecological niche is a role. So how to visualize an ecological niche, or basically how to map the suitable habitats. Mapping habitats can be done with GIS and can be integrated with remote sensing to learn a lot about the habitats of the species. We can use GIS to do that, and GIS basically stacks layers of data and find relationship between them, but geographically. In other words, we could examine abiotic relationship, which is shrimp yield, with abiotic factors. So we have the shrimp yield that interacts with salinity, disease, and water quality. Those abiotic factors shapes the shrimp yield in a farm, for example. Let's map that and see how GIS represent them. First, salinity would be a layer of gradients of salinity that can be classified into high salinity, medium salinity, or low salinity. So high salinity would be the light gray areas, and the medium salinity is the bluish areas. And we could see and conclude that the majority of the farm it has medium salinity. For disease incidence, we would classify the farm into high, medium, and low disease incidence. And we can see that the majority of the farm having a low disease incidence. For water quality, we see that most of the farm having an average and bad water quality. So these are the three factors on a layer in a GIS that we can relate to them how these factors are affecting the shrimp yield. We would see that the shrimp yield now, that the majority of the farm having a medium yield of shrimp, because it has an orange color, the majority is orange color, which is a medium. But we can now examine the areas that have high shrimp yield, like the greenish areas here. Those are area in the farm that is producing high shrimp yield, and it these areas is characterized by bad water quality, but low disease incidence and medium salinity. So now we understand that higher shrimp yield are coming from water with bad to average quality, with low disease incidence and medium salinity. This is how the GIS data sets looks like, and let's examine it more. GIS having data layers, they can be anything. Like for instance here, we have data on the transportation, which is basically the roads as a form of lines, and structures, points, and ortho imagery, which is a real satellite image of reality. We have also data on land cover, how the land is covered. Is it covered with urban area? Is it covered with water? And also we have data on hydrography, which is basically the water bodies and the flow of water along landscapes. We also have data on elevation, where are the low area, where is the high areas. And also we have boundaries, which is can be administrative boundaries, lines, and this area can be a state or something like that. Imagine all of this is overlapping exactly over each other geographically. Data types in GIS are two kinds. We have either vector data or raster data. Vector data are basically points, lines, or area. So points is basically the center of a point is a coordinate on the map x and y. But lines is at least 2 points that is connected, at least 2 points, and so on. It can be x number of points. And polygons are three or more points that are connected and closed. They have to be closed. This is the only difference between polygons and lines, because now polygons, you can calculate the area of a polygon, but you cannot calculate the area of a line. You can measure the length of a line. And each data type have an embedded attribute table. For instance, we have 3 points, red, blue, and green. Each one have a unique ID, and each one have the data that can be collected from the field. So for instance, here data on the roads, is it open, is it closed, and so on, of data that can be used, as we will see later on. This is an application of vector and lines. So for instance, here Egypt, we can have this as a polygon. Even the Red Sea itself is present as a polygon. And for lines, we would have the Nile River. That's a line. It has a start, it has an end, it's not connected, it's not closed. That's why it's a line, it's not a polygon. While we spoke about vectors, we can now move to rasters. Rasters are basically a grid along coordinates, which can contain two kinds of data: discrete data and continuous data. Raster data can be discrete, such as is it water or land, 0 or 1. Continuous data, these rasters can be a nightlight intensity, for example, starting from 0 up until 60. 60 represents very lit up areas, while as 0 represents very dark areas. And this is a picture for binary rasters or discrete rasters, which is basically the white is water and black is land. For a continuous raster, we would see something like that darker areas and a little bit a gradient of light along the area of Earth. And rasters composed of small pixels, and each pixel has a size. The higher the number of the pixel size, the greater the resolution of the rasters. Normally, in wildlife ecology, we would use data that has pixel size of 10 meters or 30 meters. In most applications, sometimes it reaches to 1 kilometers when the rasters are, let's say, temperature or annual mean temperature or something like that related to the climate. We would have a larger resolution. You can now explore the raster data using the Blue Marble website and to explore the nightlight data yourself on your web browser. And you can move between the years to see how the light intensity changes in certain areas. And also you can select a country and see how the light changes across the years. Also, you can learn more about raster when you explore this website, Almadak, and let's explore it together quickly to see how we learn more about rasters and how we use rasters to gain more information. When I search for Almadak, the first result would be